Hello again, everyone. Welcome to today's seminar. Today we have a very young and promising mathematician from Greece, Nikolaos Pallikarakis. And today Nikolaos is going to talk about inverse spectral problems for classic and modified transmission eigenvalues. Nikolaos, thank you very much for being with us today. And we are listening to you.
Aisha, thanks for the introduction and the kind words. Hello, everyone. Allow me to introduce myself. I'm Nikolaos Pallikarakis. I am a postdoctoral researcher in the Department of Mathematics of National Technical University of Athens. I completed my PhD studies in 2017 in this department under the supervision of Professor Drosos, with whom I'm still in collaboration. The subject of my PhD was in inverse problems, and specifically in the inverse transmission eigenvalue problem. And also, I'm currently working as a data analyst and computational mathematician in general in a company named NNK Technology, which is located in California, United States, and is working with metrology and non-destructive testing of semiconductors. So today we're gonna talk about inverse spectral problems, and we're gonna study two different kind of problems: so-called classic transmission eigenvalue, but also the modified transmission eigenvalue problem, which is very recently introduced. And most of the part is joint work with Professor Drosos and also with Kyriakos Stratouras. So the outline follows. I will do a brief introduction in the subject of inverse spectral problems. We're going to say a few words for the Sturm-Liouville problem, and then also introduce the audience to the inverse scattering for inhomogeneous medium, and I will associate this problem with the transmission eigenvalues. Then we're going to discuss about the inverse spectral problem for classic transmission eigenvalues in the spherical symmetric refractive index case, where we will discuss about some physical motivations, the case of the continuous refractive index, some results for this, and some more recent results when the refractive index can also include some discontinuity. Next, I will highlight the need to introduce modified transmission eigenvalues, and I will discuss about a specific problem, which is called the modified transmission eigenvalue for an artificial metamaterial background. We're going to discuss about some very recent results for this problem, and in the spherical symmetric case, we will also conclude with a new uniqueness result. And in the end, I'm going to do a summary with similarities and comparisons between these two problems. So some things probably most of you are aware of. When we're talking about inverse spectral problems, our aim is to recover physical or material in general properties of a medium from the knowledge of some spectral data. And one of the most famous and most studied problem is the inverse Sturm-Liouville eigenvalue problem, which here, for example, we see, we assume we have a string of length L. This string, assume that comes from a non-homogeneous medium with density rho of x here, and we assume that we have a problem with fixed edges at the two edge points. And if the displacement is denoted by this function u, which satisfies the wave equation, then the time-independent part satisfies the well-known Sturm-Liouville eigenvalue problem with Dirichlet conditions at the boundary. So in the inverse problem, we're interested in recovering this density, let's say, from the knowledge of the spectra. And in general, this is one of the first problems that it was studied, and there are several works on this problem. And in general, there is non-uniqueness, and under some specific cases, one can uniquely determine the density from the knowledge of the spectrum. Let us now see the scattering problem. So we assume that we are in vacuum, and we have a non-homogeneous medium inside the vacuum, which is denoted with this medium D, which has a refractive index denoted with n of x, and this is an inhomogeneous medium which is isotropic. And when we have an incident field traveling through the medium, when this field meets the inhomogeneity, it scatters and gives us a scatter field. So this problem is well known and satisfies the non-homogeneous Helmholtz equation here, where the total field, which is the sum of the scattered and the incident field, also satisfies the scatter field. Satisfies the Sommerfeld radiation condition away of the scatterer. And as far the refractive index here in general, in the most general case, one may assume that it's a bounded L-infinity function, and outside of the non-homogeneous medium is everywhere equal to 1. So in the dark problem, one tries to prove the existence of solutions of the Helmholtz equation, uniqueness of solutions, and stability, and in general, the solutions live in H1 log function Sobolev space. But in the inverse problem, which are more interesting and more challenging usually, one tries to recover the boundary, which can be unknown, and also the refractive index from scattering data, and this is in general an ill-posed problem. So next, let us see how this scattering problem is associated with the so-called transmission eigenvalues. In the special case where the incident field is a plane wave, so it can be represented as this exponential function here, the corresponding scatter field is well known that satisfies this asymptotic formula away from the scatterer, where here this U infinity is the so-called far field pattern, and this is an integral given by this formula here for x hat being in the unit sphere of Rd, where Rd is the domain where the inhomogeneity is embedded. So the superposition of these infinite far fields define the so-called far field operator. This is an operator between L2 and L2, and is given by this integral here in the bottom. So when the researchers studied the properties of this operator, it came to this result that this operator can be injective and with dense range if and only if this k squared, which I omitted to say that k squared for us is the wave number of the wave that travels. So if this wave number is not a transmission eigenvalue for a pair of solutions W and V which solve the interior transmission problem, then this far field operator is injective and has dense range. And this interior transmission problem is the following: is a set of differential equations of Helmholtz type defined D, and with the corresponding transmission conditions on the boundary. So K is the complex values of K for which there exist non-trivial solutions of this system are the transmission eigenvalues. And in the most abstract case, these are complex values, and W and V are square integrable functions, and their difference belongs in the Sobolev space H02. So this problem is a non-standard, non-self-adjoint eigenvalue problem because it is shown that it can be written as an equivalent fourth order eigenvalue problem for a compact but not self-adjoint operator. So even in abstract spaces and general domains with smooth boundary, so this also holds for the spherical symmetric cases, it's a non-self-adjoint eigenvalue problem. And as I said before, when K is not a transmission eigenvalue, the far field operator is injective and invertible, and thus it can be used to recover the boundary with sampling methods. This was the first attempt to solve the inverse problem of recovering the boundary. So since we are trying to avoid, in this case, we're trying to avoid transmission eigenvalues, not to use them somehow, the research was focused on existence and discreteness of the spectrum, because if it is indeed discrete, it can be avoided, so it can be used for sampling methods. So this it was a difficult problem, and it was completely solved in 2010 in this paper of Tsakoni, Kitidis, and Hadar, where they show that this problem has indeed an infinite discrete spectrum, provided that the refractive index is either greater or lower than 1. It cannot be one inside the domain. So next, we're gonna pass to the inverse spectral problem, where we try to use the spectral information. And there are some motivations for this problem. Firstly, real transmission eigenvalues can be measured from scattered data. This was proven in some papers. I refer here the first of these due to Chaconi, Colton, and Hadar in 2010. And also, it was proven that transmission eigenvalues carry information about the material properties. And this is what we're really interested in the inverse problems. And I refer to the paper of Chaconi, Kayora, and Colton 2008. And also the PhD thesis of Isaac Harris for non-destructive testing of anisotropic materials. So in the inverse spectral problem, since it's possible to define it, we want to determine the refractive index from transmission eigenvalues, and this is an ill-posed problem. And especially we're interested in uniqueness of this problem, and mainly today we're gonna discuss about uniqueness results. And the question is whether, under the knowledge of transmission eigenvalues, one can uniquely determine the refractive index. So now we're gonna restrict ourselves in the special case where the domain is a sphere and it's the unit ball of R3. And for these slices, we assume that the refractive index is continuous. So in this special case, we can apply separation of variables in the system of Helmholtz equations. And so the solution, the eigenfunction can be represented as infinite series of spherical harmonics, and assuming azimuthal symmetry, these are simplified in the following forms, where J of L here gonna be the spherical Bessel function, P of L is gonna be Legendre polynomials, and this function Y of R is the radial component of the eigenfunction W, and satisfies this differential equation here together with this initial condition. So this differential equation is we're gonna study this equation for values of L being 0 or higher order, but when it's of higher order, this is a singular part in the differential equation, and also this initial condition is actually imposed to secure us that the function of YL at origin is going to be equal to 0. So using this and imposing these solutions in the transmission boundary conditions, we conclude that the complex values of K we are looking for, the transmission eigenvalues, are roots of this determinant, and this determinant is the solution of the boundary conditions. So the complex values of K are transmission eigenvalues if and only if are also roots of this function, which is going to be the characteristic function of the problem because its roots are the desired transmission eigenvalues. So if we look at it all together, we have introduced a boundary value problem for YOL because we have one condition in one edge and the second condition at the right edge, because here the values of radius is 1. This equation is at the right endpoint of the boundary. And the spectral parameter K for us for this problem appears in the right boundary condition from this determinant. So for the direct problem, the first results about existence and discreteness in the spherical symmetric case were in the beginning of 90s due to the results of Colton, Monk, and Paivarinta. And for the inverse problem, the first uniqueness result was due to McLaughlin and Polyakov in 1994 in the special case where we assume the knowledge of eigenvalues corresponding only to L equal to 0. We're gonna discuss about cases today, L being 0 or not. And this is the special case where L is equal to 0 and the eigenfunction are also spherically symmetric. But this result was under some strong restrictions on the values of the refractive index. Some years later, some further uniqueness results appear. First is the result of the paper of Chaconi, Colton, in 2010, which says that given the value of the refractive index at the origin, and provided that the refractive index is either higher or lower than 1, the refractive index can be uniquely determined by the knowledge of all transmission eigenvalues. And here we assume knowledge for all infinite sequences of all orders. And also we assume that the refractive index is set to function. Also, there's another, 1 year later, another paper from Gididis and Papanikolaou, but for the special case of spherical symmetric L equal to 0 eigenvalues, under the assumption that the refractive index is C1, but also with a restriction in the values of a refractive index in the following sense, that this quantity here, this will gonna be denoted with capital A, is gonna be less than 1. This somehow is like assuming that the average of the refractive index is lower than 1, and has a physical meaning as a travel time, let's say, for a wave to move from 0 to 1. And after this, several results also appear, and this is ongoing. There's going to be a huge list if I could reference everything here. But for example, I refer to the work of Colton and Jung in 2013 for complex eigenvalues and the problem. The work of Buterin, Young, and Yurgo from 2015, which answered an open question that was remaining in this theorem of Gididis and Papanikolaou. Some recent work from Bondarego and Buterin for the stability and solvability of the inverse problem, and the list is ongoing. Now we're gonna pass to the case of spherical symmetric and discontinuous refractive index. These results can be found in a paper we have with Ross Gididis in 2017, and also in my PhD thesis with more details. So here we impose a discontinuity condition in the refractive index. We assume that the refractive index is piecewise C2, with D between 0 and 1 being the position of the discontinuity, and also we assume that outside the medium, the refractive index is equally 1, and this is done smoothly in 1. And we impose the following jump conditions at the refractive index. We introduce these constants A and B, which secure that the refractive index is going to be discontinuous. And this is generally the typical jump conditions imposed in discontinuous eigenvalue problems. So briefly, some ideas we follow here. First, we have to transform the problem into a more convenient form, and this is done through the Liouville transformation. So instead of being in values of R, now we're being in values of C here, and this transforms the differential equation into a more convenient form, where here this potential G is, since the refractive index is piecewise C2, this is a piecewise continuous function, and is not defined is discontinuous in this d tilde, where here d tilde is the transformed travel time, in the sense that it's the transformed average until the position of the discontinuity. And again, the total travel time is this A capital A. So now we're studying a new problem for a transformed discontinuity between 0 and A, instead of being between 0 and 1. Firstly, we saw that this Z is discontinuous at psi equal d tilde, and satisfies these jump conditions where this A tilde and B tilde are functions of A and B, which are the discontinuities of the refractive index. And okay, they're combined in these rather complicated forms, although this secure that our solution is going to be discontinuous. I would like to say a few words about the asymptotics of the characteristic functions, because this is one of the most important parts of this type of problems. And I recall that in the continuous case that we discussed before, in the special case where we look only the spherically symmetric zero-order eigenvalues, the characteristic function satisfies this relation for Lance values of the wave number, where we hear that the dominant, the slowest part, behaves like sine k versus k, and this also holds for the higher orders. And in this work we proved that in the discontinuous case, a similar type of asymptotics can be are proven to hold. Well, here we see that two sign functions appear, where in the second the transformed discontinuity appears, and also we see that here the A tilde of the transformed jump of the eigenfunction also appears. And these are proved using the definition of the characteristic function and the Volterra integral equations of Z of C, because using the Liouville transformation, we can also define the corresponding Volterra integral equations for Z. So one last thing here that easily can be checked, that in case where A tilde is 1, this problem, these asymptotic formulas are equivalent with this, because only the first signs remain. And now, starting to the inverse, when we studied the inverse problem, we derived the following unique results. Firstly, we looked only for the spherically symmetric eigenfunctions for order 0, and the best we could get was the following theorem that says that under the knowledge of this subsequence of eigenvalues, the constants d tilde and a tilde, which are the transformed discontinuity and the transformed jump, can be uniquely determined in two cases. If the travel time is small enough, no matter where is the position of the discontinuity, but if it's higher than 1, then we have to look for sub-intervals to derive the uniqueness. But unfortunately, we couldn't get something more. And with simple words, if we assume that we have two discontinuous refractive index and their corresponding spatial eigenvalues for 0 order are equal, then the jumps must occur at the same point. This is more or less what we get here. And next, using all eigenvalues for all infinite sequences of L, we got the following uniqueness result. That is the global uniqueness of the problem. It says that in the piecewise set2 function, the refractive index, a piecewise set2 refractive index with the jump condition we show, and if the refractive index is either greater or lower than 1, the refractive index is uniquely determined by the knowledge of all eigenvalues, if also the value at the origin is known. And the proof is based on Hadamard's factorization theorem, because we prove that the characteristic functions are entire functions of k square. We had also to use Moon's theorem, and we also used some ideas of the celebrated paper of Ole Hart for discontinuous Liouville problems, because the setting, even if it's a non-self-adjoint problem, the one we studied, have similarities. So at this point, I conclude the part of the classic transmission eigenvalue problem, and I'm gonna pass to the so-called modified transmission eigenvalue problem. And firstly, I want to show you the necessity of introducing modified transmission problems. And this came from the application, because there are some limitations on using the transmission eigenvalues in non-destructive testing. First of all, as I said in the introduction, we can use far-field measurements to detect the position of the transmission eigenvalues, but this is possible only for real eigenvalues. And since this problem is complex, is non-self-adjoint, also complex eigenvalues exist. So there are cases that, for example, real eigenvalues might not exist at all if the medium is absorbing. And second, and also really important, is that since transmission eigenvalues are associated with the material properties, we don't a priori know the wavelengths, the frequencies where we're gonna look to in order to use the far-field equations and measure the eigenvalues. So in practice, this means that we have to use infinite or a lot of different intervals of frequencies and look at these intervals for the eigenvalues. So an idea came recently that is the following: one could try to modify the far-field operator so that the wave number will be fixed and won't be the spectral parameter. So another parameter should be introduced with the role of the signature eigenvalue, well, signature in the sense of what is associated with the material properties. And the first result in this direction were due to these papers, first to Ciacconi, Colton, Meng, and Monk, and Kogar, Colton, Meng, and Monk in 2016 and 17, where in these works, they were introduced two different types of problem. The first one was a Steklov type eigenvalue problem, which is not the case of the study we are discussing tomorrow. And the second is the so-called modified transmission eigenvalue problem, and especially when this is embedded in an artificial new medium. So, especially in this case, we study the so-called modified interior transmission eigenvalue problem for an artificial metamaterial background. So, okay, maybe this sounds a bit complicated, but it's not so much. The idea is that we have the homogeneous medium, and we assume that it's embedded into another medium, which is a metamaterial, in the sense that its corresponding refractive index, which is going to be denoted with minus eta 0 of x versus a, where these quantities here are positive, so this is negative value. And since this is negative valued, this can be interpreted as a metamaterial. But I have to note here that this is artificially introduced. Is a mathematical construction we did. It's not associated with the scattering problem. It's something that it's imposed in the problem, so it's gonna make it easier to study. And the corresponding interior transmission eigenvalue problem here is the following: is again the set of the Helmholtz equations. Again, we have transmission conditions at the boundary, but new parameters appear. This minus a and eta 0 are the metamaterial properties we said initially, and since k squared is fixed, now the lambda is the new specular parameter. So we fix k, and we are looking for values of lambda. And the first result in this problem was due to Odibert, Chacon, and Hadar 2017, where in their paper they proved that also these type of eigenvalues can also be measured from far-field data. So indeed, it's useful to study this problem because it can be chosen instead of the classic one for reconstructions or for target identification or for non-destructive testing. So in the following, I present some results in the paper we had with Dros Gididis and Kyriakos Stratouras in this case of the artificial metamaterial background. And this result, I have to note that these are for general domains. I haven't assumed any symmetries so long, and are the general existence result for this problem. And in this paper, we prove that there exists an equivalent compact self-adjoint and injective operator between L2 and L2 for this modified interior transmission problem I said before. And this establishes the existence of infinitely discrete eigenvalues, which also have to be real valued because the problem is self-adjoint. And also, under a coercivity constraint, a smallest constraint on the wave number, we prove that at most finite of them can be positive. And the rest of the spectrum converges to minus infinity. Also, in this paper, we derive this unique result for general, again, domains that under this coercivity constraint, a constant refractive index of general shape is uniquely determined by the knowledge of the largest of the first modified transmission eigenvalue. So next, we're going to restrict ourselves in the spherical symmetric case again, and study this problem for these specific cases. These are based on results of our latest paper with Dros Gididis and Kyriakos Stratouras in inverse problems. It was published a few months ago. And again, since we are restricted to the unit ball of R3, we can use separation of variables, again, represent the solutions as infinite series of spherical infinite series, and assuming azimuthal symmetry, our eigenfunctions have the following forms, where here J of L again are the Bessel functions, P of L are still the Legendre polynomials, and here one can see that in the argument of the Bessel function, this lambda appears in this square root. So we have to study also this, the sign of this quantity here. And again, the radial part of the differential equation satisfies the same the same differential equation with the same initial condition. And using again the boundary, the modified transmission, the modified boundary transmission conditions, we concluded that our lambdas being real valued are modified transmission eigenvalues if and only if they are roots of this determinant. And this determinant is derived through the boundary conditions, but only in the case where lambda is not zero. Also had this strange result that in the special case where lambda is zero, it may or may not be an eigenvalue, because the system of equations is simplified when lambda is zero, but zero will be an eigenvalue if and only if it's a root of this type of Robin type, let's say, boundary condition. This is not the case for the classic problem, because in the classic transmission problem, k square, where there is the spectral parameter, is always a root of the characteristic function, and it's in general a trivial case. So again, I have to note that for the problem that we study now, the modified problem, the k is fixed and the spectral parameter is lambda, and it's involved only in the argument of Bessel functions and not in the argument of functions YL. And this is not the case of the classic transmission eigenvalues, where in the corresponding determinant in the classic problem, k square lives in all terms here. Here, lambda, with the new parameter, lives only in the Bessel function. These functions are not associated with lambda directly. And this is one of the major differences. So again, we followed similar ideas, trying to prove the existence of the spectrum in this case. So when the refractive index is C1 function and the values of lambda are negative, we have these asymptotic forms. Firstly, for the special eigenvalues of zero order, where the characteristic function behave like this for large values of absolute abs lambda, and here this is positive, and a similar condition for higher orders. But when lambda can be positive, lambda being a root is equivalent of being a solution of this equation here for zero order, and for this equation here for higher orders, where this I of L here are modified spherical Bessel functions. These equations derived from the characteristic function by imposing the complex part of the spherical Bessel functions. And one here can directly see that the left-hand side of these equations are associated with lambda, and these are constants, are irrelevant of lambda. And both of them are monotone functions, and we prove that also this is monotone. And so we use this to study the existence of positive eigenvalues. And these functions here are well defined, provided that k square is not a Dirichlet eigenvalue for the refractive index. If k square happens to be a Dirichlet eigenvalue, then for positive values of lambda, the functions cannot be zero, so we are just left in the negative. We are left only with the negative eigenvalues. And I said if k square happens to be a Dirichlet eigenvalue, because since we are studying inverse problems, we don't a priori know the refractive index, and so we cannot know if a value is a Dirichlet eigenvalue or not of the specific index. But as far as studying existence, this wasn't a problem. So using the above results, we concluded the following: that in the special case of spherical symmetric eigenfunctions, there exists infinite negative and at most one positive, and for all higher orders, still exists infinite negative, but at most finite positive. And this is okay with the theory of existence in the general case. And the proof, especially for the second one, are based using the asymptotic properties of YL of 1, because this appears in the boundary condition in the characteristic function, together with asymptotic formulas of spherical Bessel and modified spherical Bessel functions. Okay, and also before we go to the inverse problem, a straight's existence results appear. What happens if the refractive index is equal to 1? Physically meaning this is the vacuum. We have embedded the vacuum inside the vacuum, but since we have defined this artificial metamaterial domain, this is a well-defined eigenvalue problem. And in the classic transmission eigenvalue problem, when the refractive index is equivalent to 1, then the characteristic function is equivalent to 0, and this is a general case because every complex number can be an eigenvalue, so it degenerates. But in our problem, this is not the case because the eigenfunction W has this form, and the corresponding determinant has this form here with this Bessel function, which for negative lambdas has infinite discrete roots because it's a vibrating function. So unfortunately, here we're in the position that vacuum and the vacuum and the inhomogeneity can produce eigenvalues, and this is a problem in inverse problem because if we cannot distinguish the vacuum from the medium, this is useless. So of course, and for that reason, studying uniqueness is really important because if uniqueness is proved, then one spectrum can distinguish the vacuum and the non-homogeneity. So here is the question: can we uniquely determine the refractive index from the knowledge of modified transmission eigenvalues? And studying this, firstly, we derive this uniqueness result for boundary Cauchy data. We assume that we have two refractive indices that now are just continuous functions, which are distinct, and both satisfies the modified problem for the same constants a and eta 0. As I said before, this is artificially introduced at the problem initially, so they are given for the inverse problem. And also we assume that k squared is not a Dirichlet eigenvalue for both of them. And when for each order, each characteristic function of its refractive index has a common root, then the corresponding Cauchy boundary data and the fractions of the boundary Cauchy data are equal. And in simple words, this means that for every order, the fraction of the Cauchy data can be uniquely determined by the knowledge of only one modified transmission eigenvalue, and this can be done for each order separately. The proof was based on using the definition of the characteristic function as a piecewise function, as I said initially, the determinant and the simple case of a lambda being equal to 0, and the properties of Bessel functions. So at this point, looking at only one order, the best we can get is just the Cauchy function. So we have to turn ourselves again in assuming knowledge for every order. And here we have to impose the following assumptions to proceed. First, as I said before, the refractive index is continuous, and we assume that it's bounded by a predetermined constant a. Maybe it wasn't a good notation. I don't want to get confused with the travel time we discussed in the beginning. It's just a positive constant. And also the wave number, we assume that belongs in this interval here, where this k0 square of b is the first Dirichlet eigenvalue of the ball. So it's for the unit ball, it's p squared. So we restrict ourselves in relatively small, let's say, wave numbers, being smaller than p squared versus this predetermined constant, which is the upper bound of the refractive index. Under these assumptions, we prove the following lemma that the refractive index, if the refractive index and the wave number satisfy these assumptions, then k squared is not a Dirichlet eigenvalue for the non-homogeneous Helmholtz equation in the ball. And this is direct consequence of the Courant physics characterization of the first Dirichlet eigenvalue. So under this assumption, k squared cannot be a Dirichlet eigenvalue. So we can use the previous results. And now we introduce the corresponding non-homogeneous Dirichlet problem, which is the non-homogeneous Helmholtz with the non-homogeneous boundary condition. And as I said before, since k squared is not a Dirichlet eigenvalue, the above is well posed, the non-homogeneous problem. And since it's well posed, we can also define the corresponding Dirichlet-Neumann operator. And this means that the map between these boundary Sobolev spaces is well defined, and this maps the boundary condition, the Dirichlet boundary condition H, to the Neumann condition of this WH, where this WH satisfies the non-homogeneous problem. Given this, we concluded this interesting theorem that if we have two distinct continuous refractive indices, both satisfying this modified problem for some positive constants, and both are lower than this predetermined constant A, which can be as large enough. There's no restriction in its order. And also, if the wave number is small enough, is in this interval, so it's not a Dirichlet eigenvalue for either of this problem, and at least one modified transmission eigenvalue coincides for each order, which is the assumption of the uniqueness theorem for Cauchy, that I said before for the Cauchy data, then the corresponding Dirichlet-Neumann maps are identical. And the proof is based using the equality of boundary Cauchy data, because from these assumptions, the uniqueness theorem I showed previously for the Cauchy data holds. So we have equality of the boundary Cauchy data, and we can represent the solutions of each refractive index as series doing separation of variables, because we are in a ball, and apply the properties of trace operator and its derivative. And this will give us in the end the quality of the Dirichlet-Neumann maps. And using this, we included the desired uniqueness theorem, which follows. We assume that, again, we have this distinct continuous refractive index, both bounded by a predetermined constant, and wave number being small enough, not a Dirichlet eigenvalue. If there exists a sequence, an infinite sequence for each, if there exists a sequence of infinite transmission eigenvalues for each order being equal for each corresponding refractive index, then we can conclude that the refractive index are also equal. And this proof is based on the previous theorem of equality of Dirichlet nominal operators, and we used an old result from this paper of Nachman, Sylvester, and Ullman. It's a very well-known paper back to 1988 for the Borg-Levinson theorem. It was in this paper, but it applied in our case, which is simpler as well. And now at this point, as a type of summary, I would like to discuss about the similarities and the differences of these problems, and especially for the spherical symmetric case. So before that, I want to note that, of course, these problems are different in nature, as we discussed about different spectral parameters, different assumptions, although I think it's interesting to see them together and do some comparisons. Firstly, for the direct problem, and I'm always talking about only the spherical symmetric case. So for the direct problem of the classic transmission eigenvalues, the spectral parameter coincides with the wave number. It's always this k or k squared, depending on the definition. And this problem is non-self-adjoint and exists. There exists real, positive, and complex eigenvalues. Zero is always an eigenvalue, being a trivial case, and the homogeneous medium with refractive index equal to 1 is a degenerate case. In the modified transmission problem, wave number is fixed, and lambda now is the spectral parameter. We prove that there exists real, infinite real negative, and at most finite positive, and zero can be or cannot be an eigenvalue, and also the vacuum has eigenvalues. And finally, for the inverse problem, in the classic transmission eigenvalue problem, the refractive index is assumed to be set2 or set1, depending the problem. Usually set2 is used when all eigenvalues for all orders are used, and set1 with L2 derivative is used when in the paper studying zero order inverse problem. Also, there are some restrictions which are relatively strong in the refractive index. It cannot say its signs. It should be lower than 1 or greater than 1, and in most cases also the value at the origin is required. We saw that there exists unique result for special spherical symmetric zero-order eigenvalues, and also using all eigenvalues for all infinite sequences. And there are some unique results for the discontinuous case as well. On the contrary, for the modified transmission eigenvalue problem, for the inverse problem, the refractive index can be just continuous. Also, has to be bounded by a predetermined constant, and the corresponding fixed wave number in this scattering problem has to be a Dirichlet, cannot be, sorry, a Dirichlet eigenvalue for this wave number. So we have to find ways to avoid it. Although uniqueness is not associated with the value of the origin, and this is really important, it's not associated with the sign of 1 minus n, which in the classic transmission problem, this has caused many problems in studying its properties. And so far, we checked that uniqueness holds only using all orders. And the results of our work mainly is included in this paper. The first one was the discontinuous problem, and also I refer to my PhD thesis for this. And the second was for the definition of the modified transmission eigenvalue problem in the general domains. It was in the special issue of Research Mathematical Sciences. And the latest one for the inverse spherical symmetric problem and its uniqueness in the latest paper of inverse problems. I would like to thank you for your attention, and I'm looking forward for questions and comments.
Thank you very much for the excellent talk, Nikolaos. Anyone? Any questions?
May I ask a question?
Yes, of course.
Hi, Nikolaos. It's nice to see you. By the way, I told some colleagues about this new modified transmission problem, and they were very interested in these new statements.
Thank you.
We have, with Natalia Bondarenko, we have some questions concerning this part of the talk. Maybe she asked them by herself. And I have one more question about the first part of the talk. You said at the beginning that usually inverse transmission eigenvalue problem is considered as ill-posed problem.
Mm-hmm.
What I would ask, in which sense? In which sense?
In the sense that, at least for the inverse part, for that uniqueness is not direct. I mean, it can be we can have uniqueness or cannot have uniqueness depending assumptions on the refractive index, which can be very strong sometimes, especially in the first papers. I'm sure you're aware of from McLaughlin, and the results after that, the restrictions were very hard. So since it's not direct, at least at this sense, one can assume that it belongs in this category of problems. And also for the stability, and the stability not in the theoretical part, I mean in numerical methods as well. It's really difficult to secure stability for the inverse, for the numerical solution of the inverse problem, because since since uniqueness doesn't hold for general domains, it's not easy, and from my experience in this type of numerical methods, it's not easy to recover and reconstruct refractive indices from some parts of the spectrum, or without also imposing symmetries or things like this in the refractive index. So it's not directly associated with the spherical symmetric case. It's a more global characteristic, I think, of the inverse transmission eigenvalue problem, and not directly for the spherical symmetric case. I hope it answered your question, but you can proceed.
Okay, thank you. No, by the way, I would ask that our work that you cited, our work with Natalia Bondarenko, 2017, so we proved that inverse transmission eigenvalue problem is well posed, at least in the state of McLaughlin and Pallikarakis. So we proved, we established local solvability and in parallel also stability of this problem. And there are also other works in this direction. For example, that work you know too, our work with Maria Kuznetsova and Abdon Edi Choki-Rivera, where we proved in some another statement also stability, also local solvability. And there are also a series of works, recent works in this, just published in this year of our Chinese colleagues, some papers belonging to Professor Chuan-Fu Yang, for example, and Xiao Chang Su. And they also study stability questions. And at my personal, you see, of course, if the solution of this a problem in some statement may not exist, then of course there will be no stability. But after refining the statement, after refining the input data, and when one achieves solvability in one or another sense, my deep belief that stability will be always. So each reasonably stated, if each reasonably stated problem would be inverse spectral problem would be transmission would be always stable. So it's my hypothesis. So I don't see how it can be violated, stability. So such comment. And I'm sorry, I have one more question. Not even question, some small remark. In one of the first theorems you showed us, there were minimal conditions on the refractive index. Could you please find this?
For the modified or for the class?
No, so some classic. One of the first theorems, there were the case when n is from
this one.
This one, yes. I would give some small comment. You see, this central line, n is C1, and n2 item is L2. But usually reconstruction of this n goes via the second derivative. So I mean, if you want to recover the function n, then first you recover its second derivative, because this corresponds to the potential in the canonical Sturm-Liouville equation. So and there is also such marvelous function that is called counter staircase. And if the function, if n item is counter staircase, then n2 item is 0.
And in the canonical form, the potential is in which space it will be?
L2.
In L2, okay.
L2. But I'm not now about the canonical case. I mean just these conditions. If n is differentiable and its derivative is continuous, but this derivative can be counter function. Counter staircase function. And in this case, its derivative, the second derivative of n, would be 0. So, and this means that the second derivative of n carries no information about the function n.
Okay.
So this means that in order to reconstruct n uniquely, one should always assume that the first derivative of n is absolutely continuous function.
Okay, it's interesting.
Thank you, Sergey.
So thank you very much. So
Thank you.
I'm over. Thank you.
Natalia?
May I also make a comment and ask some questions?
Sure, sure.
First of all, I'd like to comment this point because I just think that now many researchers study Sturm-Liouville operators with distribution coefficients. Maybe here it's also applicable. Maybe we can take n of some class of less smoothness.
Yeah.
Sergey, didn't you think about that?
About what?
About considering the Sturm-Liouville problem with distribution potential, and then this n also will be of less smoothness.
Probably.
Yes, maybe, but there one should establish, first of all, one should establish connection between n from w. In this case, maybe one can consider n from w to 1. So
I'm not sure. One should check.
But yes, but one should check. Yes.
Okay, I have questions related to the modified intertransmission Argymaillian problem. Could you show it, please?
Yeah.
Here, why there is minus a? Why it's negative?
Yeah, this is a good question. Actually, this negative sign here is what gave us the self-adjointness problem. In the study of the general domain, where in this paper, firstly, where in this paper this was 1. If this was constant, next we posed it as a variable function. This minus 1 makes the corresponding operator, which the operator comes from the variational formulation of the problem. And when you define this operator, it will be self-adjoint due to this sign of minus a. So for that reason, we're talking about the metamaterial. This was necessary to make this problem easier to solve and have a smoother and nicer properties than the classic non-self-adjoint problem.
I see. And this function eta 0, it's positive, right?
Yeah, this is positive. And in the general setting we have here, it can be L infinity as well, just bounded, the absolutely bounded function. But for the spherical symmetric case, we assume it's a constant, because otherwise we cannot proceed with separation of variables, because there's gonna be two functions in the argument, and we cannot impose separation of variables.
So do you mean that in general, this negative sign is not important in your statement?
No, the negative sign is very important, because without it, without the negative sign, we cannot prove even the existence of the spectrum. It's it's not simplified. We started with a difficult problem. We'll stay with a difficult problem. But as for the refractive index of the metamaterials, you said, no, it's not really important and can be even constant for our case. But being variable was the most relaxed conditions defining the problem. In the spherical symmetric case, this is constant. Both A and eta are positive constants.
I see. And does this negative sign of A does it have any physical meaning? I mean, for example, can one consider plus A? Will it does it make sense from the physical point of view? So,
as I try to explain, this problem is artificially imposed. There are parameters that we plug in the differential equations to make it solvable with self-adjoint properties and with nice smoothness. Without the negative sign, this artificial problem wouldn't work. So physically meaning, it's a metamaterial in the sense that the embedded domain, which now has the same, both are D. I mean, the refractive index and the metamaterial both live in D. There is setting with different domains, but in this setting, this has a physical meaning as a metamaterial, but it's not. It's artificially, so it's not associated with the physical part of the scattering. So it could be anything. You can put a constant here, a fixed value if you want. This is the more abstract setting of this problem. So yeah, a positive alpha wouldn't change. Okay, then we would have a metamaterial. We would have another inhomogeneous material, but then what we would do? I mean, if it doesn't give us something for the inverse problem or even for the direct, because even for the direct, this is not a self-adjoint problem. So
yes,
that's the spirit.
I see. I understand your answer. Thank you very much. But I think that anyway we can consider positive A. Of course, it will be not a self-adjoint problem.
Yeah.
But maybe we can choose some subclass when this problem makes sense and when it has the spectrum. Because for the standard transmission eigenvalue problem, we doesn't have this minus. We don't have this minus.
No, and
we have. Of course, this irregular problem, yes, it's a regular problem, but it can be studied. And there are many interesting results.
Yeah, of course, can be studied, but I haven't. When we studied that and tried, to see the properties without using the minus A, we wouldn't arrive to a self-adjoint problem. And another problem that worries me is that, okay, if someone defines this problem with positive A, what about far-field patterns, far-field operators? Because if this new problem is defined, which is gonna be, like a conductivity problem in the Neumann condition, what happens with scattering? Because if these eigenvalues, these eigenvalues should be proved that can be measured from scattering data, because if they're not, at least for applications, it won't be that interesting. But from mathematical point of view, of course, every problem has its beauty and every problem has its properties, which worth studying. I'm an enemy of people that think that okay, if it's not in applications, we don't care about it. In the contrary, I love research done in things that are abstract and can lead to beautiful results. But okay, one should also have in mind that these problems come from physics, from scattering physics. So one also should try ways, to recover information from the engineering, let's say, part.
Okay, thank you for interesting talk.
And one small comment: if we remove A, remove minus, then automatically we multiply modify transmission eigenvalues with -1.
Practically speaking, yes.
Yeah. No, I mean
no, it's not so, because we have the boundary condition.
Yeah, the problem is that the operator. I'm not sure that the operator is gonna. You have to check the variation from the formulation to see the operator properties. I don't think it's just so direct that they're gonna be from a few negative numbers to plus infinity the spectrum. I'm not sure. I don't think it's so direct. But okay, it's interesting.
No, just carry minus from A to lambda.
Yeah, but you have what about the boundary condition?
But the condition doesn't depend on lambda.
It depends on A.
On A, but it doesn't matter. You can leave minus in the boundary condition, but remove it.
Yes.
I still think that it's not gonna be self-adjoint. But feel free to study, and I'm sure it's gonna give interesting things.
But by the way, I have another comment.
Please.
You see, in our paper with Maria Kuznetsova and Abdon Choki-Rivera, we devoted this paper to discussion about the so-called regularity. So there are, if one consider boundary value problems, the boundary value problems in general, not only transmission, some Sturm-Liouville problem, and for differential operators of higher orders and so on, for differential operators on graphs and so on. There is such notion as regularity in sense of Bergov. And if the problem is regular, then behavior of the spectrum is, how to say, is good. When the problem is not regular, then spectrum may behave very differently. In one situation, the spectrum can be absent. In one situation, so usually spectrum has no main part. And the same situation for transmission eigenvalue problems. So in transmission eigenvalue problems, all of them are, generally speaking, irregular in the Bergov sense. That's why. The explanation is very simple, because the main part of the characteristic determinant sometimes even disappears. Sometimes it's no longer main part. So usually, for example, some characteristic function or characteristic determinant behave like its main part, but for transmission problems there is no main part, and the transmission problem will become regular only if one changes the sign. In the second boundary condition in point 1, I mean in canonical, for example, form, if one changes sign, the problem automatically becomes regular in the Bergov sense. So, and this sign corresponds to the last boundary condition on this slide. So this means if one would consider classical transmission eigenvalue problem where k is a spectrum parameter, then this sign, changing the sign in the relation of normal derivatives would make the problem may make the problem regular. But I'm not sure now. Maybe one should change the sign also in the first boundary condition on the last but one line. I'm not sure. But so in the classical situation, normal derivatives coincide, but here they have different signs. Would this affect physical problem, initial physical problem? Does it correspond to the physical statement of this problem? When normal derivatives have different signs?
I think one should check the definition of the modified far-field operator. I think since everything, everything comes from it, as I said initially that in the scatter problem, we defined the far-field operator, and this gave us the transmission eigenvalue problem. In these problems, this modified and the Steklov I said, also the far-field operator is defined, imposing this the kernel of the operator has two parts. Now, one is the classic and one is the modified. So one should check if this problem you defined and you explained to us, how it will affect the corresponding operator. I think the first thing to be checked should be that. And then you will see whether the signs of the derivatives indeed play some role in the physical part or not. I think this should be the good way to check it, in my opinion. But all these things have to be studied carefully, because it's not straightforward, in my opinion.
Okay.
May I comment this last?
Yeah, just a little one, because we
yes. Sergey, you see, if we take the sign minus in the boundary condition, then the situation is similar to the standard matching conditions for quantum graph.
Yes.
But if we take plus, it's irregular. So I think that in this problem, it's more natural to take plus A and to obtain some regular classes similarly to your work with Abdon and Masha.
Mhm.
So this was my idea.
So this means that in our work, for example, we take we have A positive, and we can take A negative. By the way, we also consider situation when A can be negative.
When A is negative, is very simple situation because
it's a regular situation.
It's a regular situation. It's similar to the quantum graph with two H's.
How do you think is this the same here?
I think it's the same. That here, if it's minus A, it's regular situation, it's self-adjoint and so on. But if it's plus A, it's a more interesting.
Okay.
Okay.
So sorry to interrupt you, Sergey and Natalia.
It's a long discussion.
Thank you very much again for the excellent talk, Nikolaos, and thank you very much for joining us, everyone. We're gonna see you again in 2 weeks. Bye.